Greetings, calculus students. I apologize for being out today. My daughter has an illness, and I'm actually not real sure when I'm going to be back at school this week. As it turns out, this is not a real good time for me to be out. Some of the material that we're getting into is a little bit more difficult, and the calculations considerably more complex. So we'll just have to do the best that we can. If you have troubles, please visit with Mrs. Wyatt or Miss Prima, or possibly even Mr. Mata, if you're needing some extra help on your calculations. Okay, so let's begin. Looking at area under a curve. Our objectives for this day: the student will learn to estimate the area under a curve. The student will demonstrate the ability to estimate the area under provided curves using the exhaustion method. Not sure if you have seen the exhaustion method before. Would not surprise me if it had gotten touched on in AB, but not explored on as deep of a level as we're going to look at it. And your essential question: can I estimate the area under a curve? All right, now over the years we've studied many polygons and have found the areas of them as well. Actually, many of the formulas that we use for the areas of basic polygons were alterations from a very basic shape, which is the rectangle. Okay, everybody knows the area of a rectangle is found by base times height, and that spawned formulas to go along with the area of a triangle, which was half of the base times the height. The trapezoid, still 1/2 times the base times the height, but since there were two different measurements for the bases, it was a sum of the bases times the height, and so on. This idea worked very well in the early days of mathematics, but in the more modern eras, it became more and more difficult and bordering on impossible in order to calculate the areas underneath of curves, what with the curved nature of the various conic sections and such. To counteract this problem, Greek mathematicians developed what has become known as the exhaustion method. And as somebody suggested the other day, does that mean it's just exhausting to do the method? And in short, yeah, it kind of is. Perhaps that's why it's named as it is. Now, since they could not calculate the exact area underneath these curves, what they did is they broke the area down as best as they could into other polygons, okay, more recognizable shapes, and specifically they used rectangles. And this is the nature of what you've done throughout probably the last several years, calculating the area of composite shapes. Since you didn't know what area, what type of a shape the figure actually was, you built or tore it down into smaller shapes that could be more easily defined. That's what we're going to be looking at today. Okay, so let's take, for example, okay, we have quadrant 1 of a graph. We are looking at something that appears to be a truncated parabola. Okay. Back in the day, they had no idea how to calculate this area, so what they did is they started to install triangles that would fit within the space that they knew that they wanted to find the area of. Now, obviously, it's not a perfect plan. As you can see, in some places, we have overages with the rectangle sticking outside of the boundaries of the curve, and in some cases, underages, where we have rectangles that do not fill the entire area of the curve, but you get the basic idea. Okay, so let's take a look at one. Approximate the area of the region under the curve of y equals -1/10 of an x squared plus 5 in quadrant 1. Now, I'm not going to take a ridiculous amount of time going through all of this. I'm going to explain it in fairly rapid succession, so you might want to or need to press pause if there's something that you need to copy down or simply want to let soak in for a moment before you move on. Okay, well, here is the curve that is being referred to in the problem in quadrant 1. Using the exhaustion method, there are some options that are available to us. What we could do is we could stay underneath the curve, which would basically mean making contact with the curve with our rectangles on the right-hand corners. Okay, but as we can easily see, the area is going to be undersized somewhat since the rectangles do not completely fill up the space underneath the curve. On the converse of that, perhaps we could use rectangles that made contact with the left-hand corner of the rectangles. Okay, but obviously we end up with the reverse problem that we had a moment ago. In this case, the area will be oversized since our rectangles are extending out from underneath the curve. Okay, so we have these two instances, and looking at the values of the endpoints of those intervals in the domain. And here's what a lot of people find to be quite challenging about the exhaustion method is figuring out how to come up with the definitions of where these endpoints are actually at. Okay. Now, obviously, we have intervals that are going on inside of our domain. We have an interval from 0 to 1, from 1 to 2, from 2 to 3, and so on. Okay. On the in the lower side of this area calculation, where it's going to be undersized, we're actually using the right-hand endpoints. So the endpoints are at 1, 2, 3, 4, 5, and 6. Okay, so we are going to be looking for a sum of 6 area calculations that are underneath this curve. So the sum of base times height. So obviously our summation goes from 1 to 6. Okay. And our width of our rectangles, or our base of our rectangles, in each of these cases is 1 unit of width. And then that would multiply by the function itself. Okay, because that would be the corresponding height depending on where you are within the interval. So negative 0.1 times I squared. So as I changes as we move through the summation, that will take us from one rectangle to another, plus 5. Doing the calculation of these 6 areas, we've got 4.9, 4.6, and so on, and we end up with an estimated area of 20.9 units squared. Now we said that we knew this would be undersized, so this would be, technically or theoretically, however you want to look at it, the smallest possible area that the area underneath the curve could consume. On the other ends of the intervals, okay, this time we would be making contact with the left corner of each of the intervals. So we would have endpoints at 0 and 1, 2, 3, 4, and 5. Once again, the result is the summation of the 6 areas that are involved. So once again, we have a summation from 1 to 6. The width of the rectangles is still 1 unit, but we're going to have to redefine the function just a little bit in order to adjust to the left side of the intervals rather than the right side of the intervals. And it's not that difficult of an adjustment because simply what we're looking at is we're looking at I minus 1 being our position within the domain. So when you are on step 1 for your summation, when I equals 1, well, we don't want to be at 1 in the domain. We want to be back at 0. So by subtracting 1, that'll shift us, gives a horizontal shift back to the left 1 unit, and that would get us positioned correctly. For interval 2, okay, you plug in the 2 for your I, and again, 2 minus 1 gets you back to 1 in the domain, and it works well for all of the values of I. Now the values that are the result of this summation are 5.0, 4.9, and so on. And we end up with an area this time of 24.5 units. But as we've already stated, we knew that this would be an oversized area. So what we're stating here is that the maximum area that could possibly be underneath the curve would be 24.5 units. So when you combine these two pieces of information, what we have determined and what they determined back in the day was that the area was somewhere between just under 21 and 24.5. Now, quite obviously, it is the width of the rectangles that is causing the margin of error to be as large as it is. So, stating the obvious, the narrower the rectangles, the more accurate the approximation will be. So let's say this time, instead of having 6 rectangles in order to define the various area underneath the curve, let's double the amount of rectangles. Okay, so here is our function once more, only this time we'll use half unit wide rectangles in order to fill our curve. You can already see, even with my crude drawing here, that the area that is not covered by the rectangles underneath the curve is already substantially smaller as far as the area that did not get covered. Okay, so from there we would simply adjust the formulas. Now this would just simply involve dealing with the width of the intervals. Our summation would now go from I going from 1 to 12, since there's 12 rectangles filling the space this time. Our width is 1/2. Okay, so let's figure out the height of the rectangle. In this case, we have our function, only we only want a half unit, so we'll put I halves. And the result of the area calculation there, I'll spare you going through all 12 of the area calculations, but it is 21.875. So that brought us almost a full unit higher up on the lower area boundary. Okay. Now, in order to get to the left-hand corners of the rectangles, okay, this time, once again, we are going to have a width of 1/2 on our interval. Okay, and I halves is still the deal, but we want that 1/2 unit phase shift in order to get our rectangles back to the left-hand corner, just like we did on the previous one. Okay, so the formula is starting to look a little crazy, and that does tend to freak a few people out. But again, this time we get a calculation of the area summation of 23.675, and that is almost a full unit smaller than we had on the upper bound of the area. Okay, so as you can see, we are homing in on a smaller margin of error for the area calculation underneath this curve. Okay. The bottom line here is obviously as the width of the rectangles continues to diminish, as it eventually diminishes to nothing, we should be zeroing in on the actual area underneath the curve. Okay. Now, a lot of times what we're looking at in calculus is not an entire curve. The range of values, or the domain of the values, has boundaries that are placed upon it, very much similar to the last curve where we were restricted only to quadrant 1. Well, perhaps the restrictions aren't just a generic space like quadrant 1, perhaps it's an actual value. We don't want to look underneath a particular numerical value in the domain, and we do not want to look above a particular value in the domain. So let's say we're looking at a curve. Once again, we're in quadrant 1, which is typically the case. A lot of times real-world application does not have much use for negative values. Okay, but let's say our graph is restricted by the gray lines that just appeared. We're only interested in the space that is existing between those two values and underneath the curve. So obviously those two boundaries are either established by, or make contact with and then established by, the x-axis, values in the domain, predetermined numbers. Okay, and then underneath the curve we have a particular area of space. Okay, so here the curve is bounded by the lines x equals a and x equals b. The interval is going to be subdivided into n equal subintervals. Okay, so let's look at an artificial interval within our interval. Okay, so a subinterval. This is what we're going to refer to as delta x. Obviously, the change in x as you move from one side of the subinterval to the other side of the subinterval. Each subinterval will be defined as having width of b minus a divided by n. Okay, so we always take the upper bound minus the lower bound because, once again, we're typically not interested in negative values. And then we will divide that width by n. We're definitely not interested in negative length measurements, so we definitely want our numerator here to be a positive number. Now, the extreme value theorem plays a part here. It guarantees that within this interval, there is a maximum value within the interval and a minimum value within the interval. Even if those values happen to be a tie with each other, there is a max and there is a min. Okay, so we have two values at the high and low points of our delta x interval. Okay, obviously you have a maximum for the function within, and there's that wonderful word again, ith subinterval. And of course we have a minimum value of the function within the ith subinterval. Ith is just an arbitrary value, meaning it does not matter which particular number interval we are looking at. The next thing that needs to happen is we need to define the difference between an inscribed rectangle within the interval and a circumscribed rectangle within the interval. Now, I'm sure you're probably familiar with these terms from before, but here they are again. Underneath the curve, within the bounds from A to B, we have a rectangle that is inscribed within the space underneath the curve. Inscribed is the fancy word, meaning it lies completely inside of the space within whatever it is you're looking at, in this case, a curve. On the other hand, our interval, its overall height could extend beyond the confines of the curve, and this is what we would call a circumscribed rectangle, because it does extend outside of the space that is being observed. So hopefully you remember inscribed and circumscribed from your previous years of mathematical work. If not, well, there's a couple new terms for you. Okay, the sum of the inscribed rectangles is what we call the lower sum. This was the result of the first calculations that we did on the first example. It's not always going to be the set of the first calculations. It simply depends on how the curve is behaving and whether or not, or just simply where your rectangles are actually going to be at here. But your inscribed rectangles is going to be your lower sum, because obviously those rectangles are going to stay inside of the curve, and you will have some interior spaces that will not be covered by the rectangles. Okay, so our lower sum, S of n, is equal to the summation from 1 to n of the function at the minimal values, m sub I. Okay, so just kind of using the lowercase notation there, whereas your circumscribed rectangles are called your upper sum. So we use capital notation here to differentiate between the lower sum and the upper sum. So capital S of n, which is the upper sum, is equal to the summation from 1 to n of the function evaluated at the larger of the values. And of course, both of those are multiplied by delta x, which is the width of your intervals. So our actual area is somewhere in between the lower sum calculations and the upper sum calculations. So let's take a look at an example. Our example is to find the upper and lower sums for the region bounded by f of x equals x squared and the x-axis, and between the artificial boundaries x equals 0 and x equals 2. Okay, so putting all of these boundaries into our thoughts, basically if we are between 0 and 2 on the x-axis and we are between a curve that is moving upwards and the x-axis itself, then we are looking at a portion of a parabola in the first quadrant. Okay, so taking a look at the graph, there goes the parent function for the quadratic, only in the first quadrant, and we are restricted between 0 and 2 on the x-axis. So this is the area that the problem is referring to. Now the calculations are extensive, so bear with me as we go through them. Okay, first off, determine a length of each subinterval. Now we said delta x, the definition would be from b to a divided by n. Well, in this particular case, our boundaries are from x equals 2 to x equals 0, the upper boundary in the domain, to the lower boundary. And of course, n is the number of subintervals that we have. And it's kind of an arbitrary number at this point. We're going to allow it to be as much as possible. So our width, or length, however you want to look at it, of your subinterval is 2 over n. Okay. Minimum values. Now obviously the minimum sum are going to be the result of rectangles positioned within the curve such that the rectangles are making contact with their left upper corners with the curve. That will keep them within the boundaries of the curve. Okay, so our little m is the result of our ith value minus 1 divided by 2 over n. Okay, so simplifying a little bit right there, distributing the 2. Maximum values obviously are going to be at the right corner of the intervals. Okay, so our values are going to look more like this. Okay, I times 2 over n, of course 2i over n. Okay, back to the lower sum. The lower sum equals the summation from 1 to n of the function multiplied by the lower m value times delta x. Plugging the values that we just had in there, we have the summation from I to the n of the function evaluated at 2 times I minus 1 over n times the delta x value 2 over n. Okay, so plugging into the function, well, the function was simply x squared. So we have this m sub I value 2 times I minus 1 over n needs to be squared because the function was x squared times 2 over n. Okay, simplifying that polynomial mess a little bit and then running the evaluation of the summation of I to n. Now 8 over n cubed is a constant because I is the index of summation. It is the I that is going to be changing values as the summation works. So we can pull the 8 out of the numerator, the n cubed out of the denominator, as they will be unaffected by the summation. Now the summation itself, we will have the summation from 1 to n of I squared. That is an identity. We'll get to that here in a moment. We will have the summation of 2i, and we will have the summation of the constant 1. Okay, so once again, the constant 8 over n cubed is simply weighting. We have a summation of I squared, which is the identity, n times n plus 1 times 2n plus 1 all over 6 minus 2 is a constant in that second term, so it can be pulled forward. And then you have the summation of I, which is an identity, n times n plus 1 over 2. And then lastly, you have the summation of a constant, and we have an identity for that, and that is the constant times the upper limit, which is n. So 1 times n is n. Now we have a whole lot of math going on right there, but none of it is really complicated math. Okay, so I've run through a whole bunch of calculations in there and simplification in order to get all the way down to this. Okay, ultimately there is a 6 that showed up in the denominator, okay, but it was able to reduce with the numerator, so the new coefficient of the problem is 4/3. The n cubed still remains in the denominator, and the rest of that mess inside of the curly brace is simplified to 2n cubed minus 3n squared plus n. Okay. Distributing and simplifying a little further, you have 8 thirds minus 4 over n plus 4 over 3n squared. This is the lower sum of the area calculation with that function using those boundaries. This is the smallest area that space could possibly be. Okay, doing the same thing with the upper sum. Okay, we end up with these calculations, which I obviously failed to expand in my PowerPoint here. Okay, but walking through it again, it's the same information. Okay, simplified a little bit differently, obviously, but we end up, well, let me see here. Oh, there's the expansion of it all. My notes are a little messed up. Okay, plugging the upper sum in to I over n times delta x, which was 2 over n. Plugging into or evaluating in the function x squared. Okay, once again, we have an 8 in the numerator that is constant, and we have an n cubed in the denominator, which is constant, so that can be factored forward. And then we have a summation of I squared. Summation of I squared is an identity. We have n times n plus 1 times 2n plus 1 all over 6. Simplifying a little bit inside of the parentheses and factoring a little bit, and then redistributing. Now I am redistributing here because it is going to make a point for itself here in just a moment. Okay, but our upper sum is 8 cubed plus 4n plus 4 over 3n squared. Okay, there are the two areas that are involved in the upper and the lower sum. What we just discovered is that the approximated area is actually between these two values. We'll notice the similarity between the values that are involved here. There's only some sign differences, and that's actually something that's going to become pretty important. Okay, now same example, assuming that you know that there are a predetermined number of subintervals. Okay, so let's say this time we are looking at 4 subintervals. Okay, and as before, it is going to be important to make sure that your upper sum and your lower sum endpoints are positioned correctly within the domain. Okay, this time delta x is not 2 over n. Okay, this time we are being forced to obey 4 subintervals. Okay, so in this case, n is not an arbitrary value, it is a known value. So our width, obviously, is going to be 1/2. We already knew what the lower and upper sum values would be. Okay, so plugging in the fact that there are 4 subintervals, that takes n out of these calculations as well. Okay, going back to the equations at hand, here's the lower sum. And the new values, using the fact that there are now 4 subintervals. Okay, we have actually end up with a 4 over a 16. I'm sorry, it's actually a 4 over a, well, goodness gracious, what is it? An 8 over a 64 is your fraction, reduces to 1/8, and that 1/8 does factor out. Okay, and then as you run the summation from I going from 1 to 4, we end up with a 0, a 1, a 4, and a 9. And clearly this simplifies all the way down to a single value. Okay, so there is our lower sum, 1 3/4. Okay, the upper sum. Okay, this time again we know that there are 4 subintervals. The problem forced us to have those 4 subintervals, so it's going to remove a lot of that extra information there. Okay, once again, we end up with a constant in that mess. It is 8 over 64, which reduces nicely to 1/8. Factor it forward, and we have a summation of I squared. I squared is an identity. Okay, but actually on that one you don't really need it since you don't have any unknown values in there, so you can just plug in your values. I squared, which 1 squared, 2 squared, 3 squared, 4 squared. Okay, so we end up once again with a value, 3 3/4. Okay, so the actual area is between 1 3/4 and 3 3/4, and that's actually a very wide margin of error. Okay, which basically means only one thing. Having 4 subintervals in this particular case was not a very good choice as far as the number of subintervals. There was too much area that was either left unmeasured or overmeasured inside of that calculation. So more subintervals would be needed, obviously, to close the distance in that gap between 1 3/4 and 3 3/4. The assignment, which I am not entirely sure, I kind of figured it would take us a couple of days to get through these notes if we were going through them one step at a time, which is fine that it would take today and tomorrow to go through those calculations, and that would leave us Wednesday to look at this assignment. But I figured with my absence I would go ahead and give you the assignment at this point. So if you did happen to go through and watch the video or possibly finish the notes today in class, that you would have the assignment and could begin working on it at your leisure. Okay. Obviously, these calculations are more drawn out, which means we're more likely to have some difficulty understanding what's going on with them. So please do seek help if I am not available. Find somebody that does have some calculus experience and see if they can't help you get through some of these calculations. Again, I apologize for my absence. I will be back in class as soon as possible.